Hello class, this is CSE-5250, sections 2 and 60, week 7, spring 2025. Alright, I guess it's about high time that we talk about OpenMP. First few weeks of class, we were looking into pthreads, which is a multi-threading library, but now we're gonna look at another multi-threading library. So, in my opinion, this one is a lot more powerful in the sense that when we were working with pthreads, we added in function calls that would create and merge threads, but it required for us to also have what is called a thread handle. We're going to look into OpenMP, which is a API, but also a set of compiler directives that allows us to write multi-threaded programs at a much higher level compared to pthreads. Higher level in the sense that we aren't working with the nitty-gritty that's much closer to the hardware, in the sense that we have high-level programming languages and low-level programming languages. You'll see what I mean. But anyway, what even is OpenMP? So, OpenMP is, as I said, it's an API for writing parallel programs, more specifically shared memory parallel programs. That is multi-threaded programs, because the nature of multi-threaded programs is we have multiple threads and they all share the same resources except for any private variables that the threads may have. OpenMP allows the compiler and runtime system to determine the behavior of threads, making it easier compared to pthreads to write high-performance multi-threaded programs. Because OpenMP was developed by programmers who believed that writing large-scale programs with other APIs was too difficult. So, as I said, OpenMP lets us write parallel programs at a much higher level compared to pthreads. So, with that, we can get started by writing a multi-threaded Hello World program. So, remember the multi-threaded Hello World program that we wrote in pthreads? This one here, where we wrote a dynamically allocated array of thread handles called pthread create within a for loop to create each of our threads, and then called pthread join within another for loop to join our threads back with the main thread. Yeah, remember when we had to do all that work? Well, with OpenMP, we can write an equivalent program with far less code. So, let's try that out really quick. So, per the slides, we have this Hello World program. So let's try it out really quick. So, I'll just put it in this folder for now. So, I'm going to open a terminal, but I'm also going to open up a text editor so I can start writing a Hello World program using OpenMP. So, this is not it. I need a new program. I need a brand new document. Okay, let's go. Standard io.h, include standard library.h, include omp.h. So in a OpenMP program, you need the omp.h header. That's where all our OpenMP related functions live. Let's add in the code for our hello function. Void, return type void hello, and then void in parentheses. That is our hello function. This is our main function. Int main, int argc, character star argv. Square brackets. Let me just add the last line of code here. Return 0. Now let's get to work with the rest of the program. So I'm going to say int thread count equals strtoll argv1 null 10. If you recall from when we were working with pthreads, this function here parses a command line argument. It's here to parse one of our command line arguments into a number. So argv1 is going to be the number of threads we want our program to run with. Null, just leave that as null. And 10 is, we parse our value as a base 10 number. Okay, so how do we make our threads? Is there a function that we have to call to make our threads? And the answer is no. It is a simple pragma line. So that is pragma OMP parallel. And that's it. Well, actually, that's not quite it. Not for this hello world program that we're writing. I'm going to add an extra clause, and that is num threads, and in parentheses, thread count. And then one line next, and hello. So that is our hello world program right there. Let's save this code. I'll save it in this folder, and I'm gonna call it hello. Okay. We're almost done. We just need to write that hello function. So void hello, void, and then int my rank equals OMP get thread num, and int thread count equals OMP get num threads. So these are two functions with nearly identical names. One is called get thread number, and the other is get number of threads. OMP get thread num and OMP get num threads. You have two nearly identical functions, by name at least, but they return related values. The first one is, of course, the rank of the thread. So we create threads in a specific order, starting from we create threads and we enumerate them from 0 to some maximum value. So we have a thread 0, thread 1, thread 2, thread 3, and so forth. The thread count is basically how many threads are we making. So if you have a thread 0, 1, 2, and 3, we have 4 threads. So we can have thread 0, 1, 2, and 3 out of 4 threads total. We're going to use these two values to say our hello world method. So printf hello world from thread %d of %d exclamation point end line closing quotation mark comma my rank and thread count, and then that's it. All right, so that is our hello world program, right then and there, the entirety of it. Let's try it out. So for us to compile our program, it is a slightly different command, and we'll write it as follows: gcc-g wall -f OpenMP -o, the name of our program. I called it hello. Okay, so that's the name of the executable that we want, and then the name of the source code file, hello.c. Press enter, and there we go. So remember, as to reiterate, the command was gcc-g -wall -f OpenMP -o, the name for our executable, and the name of our source code file. That's it. Oh, and by the way, one other thing. We are not restricted to just C code here. You can do this in C++ if you wanted to. If you wanted to compile this as not a C file, but if you want to work with C++ with this, you can. The difference is you would use a .cpp file, and then the compile command would instead be G++. If I did that instead, it still works. So yeah, you can either work with C or C++. The textbook has us work strictly with C, but in my experience, it also works with C++. Yeah, let's just stick with C just to be consistent. I will make one exception to that, and I'll show it to you a little bit later, and it's the fact that you can work on the OpenMP assignments on a Windows machine if you wanted to. I'll show you how you would do that in a little bit. So, either way, we now have a executable program that we can run. So let's do /hello, and we get a segfault because I never passed in a number of threads we want to run with, but let's do that really quick. So /hello, let's do 10 threads, and there we go. Hello world from thread 5 of 10, 0 of 10, 1 of 10, so on and so forth. Pretty simple, right? So what about this code? It's much cleaner. So what about this code makes it so much shorter compared to this code? Well, for starters, there are no special functions that we have to write in to OpenMP, in an OpenMP-based program, that requires we wrote no such functions that had, we wrote no such functions where we had to create a thread. All we did was create a parallel section of code, and this is the parallel section of code. So, writing this pragma line, pragma OMP parallel, implicitly creates a team of threads. They all run the same function, and they merge back together. So, let's pull up the slides for some more details. So, of course, when we run a program, we're gonna say hello /hello 4, and they're not gonna be in order because they're competing for access to standard output. Also, if we have more threads than there are CPU cores available on the system, they're also gonna compete for CPU cores. So there is no guarantee that our output will be in order unless we add a means of synchronizing the threads. They're gonna be in some random-ish order. Not unlike how we had our pthreads program also outputting in a random-ish order, at least with our Hello World program. So, as I said, if you want to work on these labs in Visual Studio on Windows, you can now. Alright, so to demonstrate that, we're gonna have to open a Visual Studio project. So I'm gonna open a quick one. I'm gonna open a brand new Visual Studio project on my Windows machine, while in the background I have my Ubuntu guest running in the background. So I'll create a new project. Let's call this OpenMP Hello, and I'll go with an empty project. Click Next. Let's call it. Let me put it in a good location. So. OMP Hello, Spring 2025. Press Enter, and alright, now we have the same program. No, now we have the interface for Visual Studio. I'll right click on Source Files and click Add, New Item, select the CPP file, and we're gonna name it main.cpp. As I said, you can work with OpenMP in either a C program or a C++ program. They will both work either way. If you go with C++, the advantage there is that you have access to all the data structures that C++ has to offer. Okay, so let's rewrite the same program. Yeah, let's rewrite the same program. So let's pull up the slides here and use this as our reference. Okay. I'm gonna zoom in because I feel like if we have such large amount of space here, you would want to see it in its full resolution. Even if you're watching this at a low resolution, I'm just hoping that this is large enough that it would compensate for any compression that might happen. Okay, let's begin. Include standard io.h, include standard library.h, include omp.h, void hello void int main int argc character star argv square brackets. There we go. Return 0 at the end, and now let's write the rest of our program. Int thread count equals str toll argv1 null 10 pound sign pragma OMP parallel. So remember that command, that directive I should say, that pragma OMP parallel directive declares a parallel section of code that is equivalent to how in pthreads we wrote a for loop that would create a bunch of threads, and then after that we would create another for loop that would join those threads back with the main thread. So I'll add hello, and that's the end of the main function. Now I can get to writing the hello world function. So void hello void, and then int my rank equals OMP get thread num int thread count equals OMP get num threads printf hello world from %thread %d of %d exclamation point new line, and then my rank thread count. There we go. And just like that, we have the entirety of our program. Now all we got to do is click the debug button, right? No, that's not how it works. The problem is the program is expecting command line arguments, and we're not passing any when we try to debug it this way. If you look at the bottom though, you may have saw it for a split second, but it said build succeeded. So for us to debug this program and allow for command line arguments to be entered, we need to run this a different way. So press Ctrl-Shift-B to build your program, and right-click the solution itself in the Solution Explorer. Select Open File in File Explorer. Now we need to find the executable file that was made. Note up here, our program is we selected a platform of x86. So that means our program is going to be in an x86 folder somewhere in our project folder here. If you selected x64, then it'll be in an x64 folder. I chose the x86 option because that's what the program chose for me. So we need to find where our executable is. So we can just look for that by typing in .exe and then looking for the executable itself. That is one way to do it. And we can do it like that if we just have to search for that in the search bar here and then click Open File Location. There we go. And now we get the path that shows where our executable was. So it was in the debug folder. So this is our solution folder. This is a debug folder, and within that debug folder, that's our executable. So I can just double click it and run it and get the same error as before. If we were going with an x64 build, the process is slightly different. So if I press Ctrl-Shift-B to build our program, if you are compiling this as a 64-bit program, your compiled executable is going to be in an x64 folder, and then a debug folder within that, and there's your executable. That is the 64-bit version of the program. If you were going with a 32-bit program, it's in a debug folder. Either way, find your executable. once you find your executable, click on the address bar. Type in PowerShell. And then, now we can run our program. So PowerShell is Windows' version of a Unix command. PowerShell is Windows' version of a Unix-like terminal. So we can use a lot of the same commands that we could in a Windows terminal, such as ls. That shows us the listing of all our files in our current directory. So I can also type in clear to clear whatever was displayed in the terminal. Well, it's PowerShell, but whatever. I'll call it a terminal anyway, even though it's kind of overloading words. But anyway, if you want to run a program, it's the same thing as before. So it's / the name of the executable. So here it is OMP hello spring 2025.exe, and we want our program to run, but we need to give it the number of threads we want to run with. So I'm going to type in 10, and it didn't work. What gives? Well, that's because we forgot to do one change to our project. Click on Project up here, click on Properties, go to C/C++, click on Language, OpenMP Support, change that to Yes, click Apply, click OK. Rebuild your program, find your executable. Again, I have the folder for that opened already, so I don't have to search for it again. But I also had the terminal here open, so I can just retype that same command. So again, if we were to do this on a Windows system, and you can, those are the steps you need to do to not only set up your project so it'll work with OpenMP, but also how to find the executable. So once again, if you want to work with Visual Studio, you need to go to Project, Properties, C/C++, Language, turn on OpenMP support. If you want to find the executable, press Ctrl-Shift-B to build your program. Right-click the solution in the Solution Explorer, open folder in File Explorer, look for the debug folder or the x64 folder, depending on whether you built it as a 32 or 64-bit program. And there's your program. Okay, so let's run this now. I already have another window here, so let's enter the same command as before. So / name of the program space the number of threads you want. Still not working. Oh, I know why. Because I built the 64-bit version of the program. Let's go back and rebuild the 32-bit version instead. There we go. That should do it. So if I type the same command again, there we go. It's running with 16 threads. And you want to know what that is? I actually forgot a line in that directive there. So it says pragma OMP parallel. What will happen if you left that alone? If you just wrote pragma OMP parallel, it will create as many threads as there are CPU cores available on your system. So if you recall, I have an AMD 8-core 16-thread CPU, so that means I can run up to 16 threads at once in parallel. So OpenMP is smart enough to run as many threads as there are available CPU cores on my system. So by default, we'll make as many threads as our system is able to handle. If you want to control that quantity, we want to add in the following clause: num threads thread count, and no semicolon, because this isn't a line of code, it's a directive. So I'm gonna build the program again. I'm gonna rerun the same program as before, and there we go. We ran it with 10 threads. Now we have a means of running the program with as many threads as we want, but at the same time, we could just default to however many threads are available on our system. If you did that, if you wanted to default to the number of threads available on the system, you would simply omit this num threads clause here. But more to the point, if we just remove this int argc character star argv, then our program is gonna run without ever requiring for the number of threads. I can drive the point home by removing this one line of code here, and then removing this clause. This will force the program to default to the number. This will force the program to default to however many threads my system is able to handle, which is 16 threads. So rebuild, clear, and we run the program. The command line argument of 10 does nothing. I can now run with however many threads my system is able to handle. For the sake of consistency, let's just run our programs, let's just write our programs so that they accept a command line argument that specifies the number of threads we wish to run with, okay? But that's how you would write the same program in Visual Studio. One more set of caveats, however, and it is the following. If you are to write this program in C++, and you can, there are some things to keep in mind. Remember IOStream? Yeah, you have access to that if you're using C++. And if you wanted to, you could use not printf, but rather cout. I would advise using cout because you get a race condition if you do. You'll see what I mean. So I'm just gonna replicate this line of code using cout instead. So that is hello world from thread There we go. So that cout line is equivalent to our printf line. We can use this, but I would advise not using it because if we do, here's what'll happen. We get a race condition if we do. See that? So we get a race condition from all of our threads trying to compete with one another to print out a single line of code to the console. So what's happening is, think about it like this. We are couting one piece at a time, but every thread is trying to output their one piece at a time. This results in a race condition where we get hello world from hello world for hello world 0 of 10. That is a race condition that we can easily avoid by, well, there are two ways to do this. You can either use printf, or you can just combine all your strings into one big string and just output the whole string as one big line. So what do I mean by that? Well, I think we need to include a string for that. So one option is to use printf instead, but if you really want to insist on using cout anyway, let's make a string. If you want to insist on using cout instead of printf, you will need to concatenate all your pieces of your string into one line, not unlike this. I am getting issues, but I think it's because I need to output it. I have to produce it like one piece at a time. So It didn't quite fix it though. You know what, just use printf. Just use printf. Okay. Now with that, yeah, just use printf. Just don't bother with cout. Just use printf instead. Much easier that way. Alright, so with that, let's get into the weeds about what's happening with the program. So, just in case, the instructions on how to build your program using Visual Studio on Windows, they're also in the slides. You need to go to the properties, turn on OpenMP support, right-click on the solution, navigate to you'll need to navigate to your executable, and you can just search for it that way. What's missing in here is the instructions on how to find your executable on a 32, if you compiled it as a 32-bit system, or no, 32 versus 64. As I mentioned, if you build your program as a 32-bit program, your program is going to be within a debug folder. If you build it as a 64-bit program, your debug folder is going to be within an x64 folder, and then there's your debug folder, and there you go. Compile it either way. Compile it however you want. Just be mindful of what platform you would be building on, because the instructions on how to find the executable are slightly different. Alright, let's talk about the program. So this program, we add a few directives. Well, there's only one directive that we're working with here. So, C and C++ directives are preceded by the word pragma, and OpenMP related directives, they start with #pragma OMP. As I mentioned, we need omp.h because that is our library that contains all of our OpenMP related functions. Much like our Hello World program for pthreads, we have our program set up to accept command line arguments. Line 9 is our strtoll function, which, as before, parses one of our command line arguments as a base 10 value. Line 11, that is our pragma OMP parallel directive. So, when we reach that parallel section of code, at the beginning, the main thread forks into what is called a team of threads. They all call the same function of hello, and they all merge back together with the main thread when they're done. Some OpenMP terms, when the program forks into multiple threads, that resulting group of threads is called a team. There's going to be a thread with an ID of 0. That was the first thread ever created. It's called the master thread, or the main thread, or whatever. It's the master/main/parent thread, because it's usually that thread that creates all the other child threads. A thread that encounters the parallel directive creates a team of threads. That thread is the parent thread. So, master/main/parent thread. A thread started by a parent thread is, of course, a child thread. At the end of our execution of our parallel block, all of our threads hit a barrier. So it's an implicit barrier because we never explicitly wrote it out. It's implicit because, well, that was implied when we wrote our parallel section. It's implied that at the beginning of the parallel section, there is a fork command, and at the end, there is a barrier. Threads that have finished their work wait at the barrier for other threads in the same team to finish, and once all threads have arrived, they join back with the main thread. Well, parent thread, whatever. So it's basically the fork and join model all over again. So one thread enters the parallel section, forks into a team of threads. They all run the same code of hello, and then they reach a barrier where they all wait for all other threads to finish. Once all threads are there, they merge back with they all merge back with the main thread. Our example program has no means of error checking, And there are a few possible issues that can happen with our Hello World program, such as we've seen already, what happens when you forget to write a command line argument as part of our command to run the program, or what happens if we enter a negative value. What can also happen is what would happen if OpenMP support is just not there. If you recall, I tried to run the program and forgot to turn on OpenMP support. If this happens, then your program's just going to run as a single-threaded program. If you, however, have that and you don't use openmp.h in your program, you'll just have compiler errors. Okay, so that's our basics on what's happening with the Hello World program. Let's take some time to work with another problem that we can parallelize, and that is the trapezoidal rule. This is going to be our first program that we're going to write in OpenMP. It's an implementation of the trapezoidal rule, a technique for approximating the value of a definite integral. So if you recall from calculus, we have some area under the curve. The curve is f of x. We want to find the area under a curve between, say, two endpoints, A and B. And of course, we can approximate that by dividing it into strips, all of the same width, and approximating the area as a sum of a bunch of trapezoids. So we have this trapezoid here, this trapezoid here, this trapezoid here, this trapezoid here. Let's pluck out one of these trapezoids and look at it really close here. The width is going to be some width, let's call it delta. The height, let's just call it AI, no, f of AI. And that's the height. Well, it's this height here. And this other height, let's call it f of BI. So we're finding the area of a whole bunch of trapezoids. Let's just call this AI and BI, which are the two heights of our trapezoid. So the area of a trapezoid is as follows. Equals, area of a trapezoid is 1/2 height 1 plus height 2 times the base. Of course, I can just rewrite it as follows, where we have this instead. So it's the average of the two heights times the base. So the geometric interpretation is putting a little pivot point here, cutting this little triangle off, rotating it around, and then putting it here. So that's a geometric interpretation of what is happening here. So we're adding a whole bunch of trapezoids together, so we have, okay, so the area of the area under the curve is approximated by trapezoids. The area of a single trapezoid is this. So we can represent the area under the curve as the sum of a bunch of trapezoids. So we can express this even with going so far as to use the sigma notation as well. But let's just keep it as simple like this. So we're adding a whole bunch of trapezoids. We can factor out the b over 2, but let's take a look. Let's not do that and see what happens if you just rearrange a few terms. So this is, well, factor out the b, and then we'll have h1 over 2 plus h2 over 2, where h1 and h2 were the heights of the two. They were the two heights of our trapezoid. So h1 over 2 and then h2 over 2. So this was this term after we factor out the b and distribute the divide over 2. We can add that to this here, so that's h2 2 over 2 plus h3 over 2 plus dot 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 plus hn minus 1 over 2 plus hn over 2. So this is why we didn't divide by 2. See these two terms? They're two halves of the same thing. There's also a h3 over 2 plus h3 over 2 over here. It's within this dot 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 here. And there's an hn minus 1 over 2, another one over here within the dot dot dot. So really we can just rearrange this thing to be h1 over 2 plus h2 plus h3 plus dot 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 plus hn minus 1 plus hn over 2. So that's just our same summation, just rearrange. So really what's going on is the area of our curve, we can just estimate that to be the sum of all the heights except the left height of the first trapezoid plus the second height of the right trapezoid. So what I mean by that is we just add all these heights together, except we add the height, add half the height of the very first height, and then add the height of the very last height. So this is just the same thing, but just rearranged. And that is what our trapezoid, that's what our trapezoid rule program is calculated. So this is just how we get to the code that we're gonna be looking at soon enough. But anyway, one other thing is, the textbook, I used height to mean these heights, but the textbook uses height to mean something else. The width of the trapezoid, confusingly enough. But the idea is still the same. The area of our trapezoid is basically just the heights of our, it's the heights of all of these endpoints here. So this here, here, here. So these heights here, we're adding all of these up, except we're cutting in half the very first height and cutting in half the very last height. We add those together and then we multiply that by how wide we made our trapezoids. All the trapezoids have the same width too. So basically when we write this out as a for loop, we just simply say something like for I equals 1, I is less than number of trapezoids minus 1, I plus plus. We add all our heights from h2, well, it's 0 index, so it's h1 to hn minus 1. We add all of them together, add half the height of h0, and add half the height of hn minus 1, because again, it's 0 index. Okay, so let me back up. In a for loop, we would add h1, h2, h3, all the way to hn minus 2. To that sum, we add half the height of h0 and half the height of hn minus 1. Combine, add all those together, and then multiply the thing by the base. That's how wide our trapezoids are, and that's how we get the area of our trapezoid. So that's how you would write that out in code. And that's how the code in our program looks. So f of a and f of b, that's the first height, that's the left height of our first trapezoid and the right height of our last trapezoid. And we're dividing it by 2. H is supposed to be the base, and that is the width of each trapezoid. So that is however long ours, so h, okay, so b minus a is of course how long our base is here, divided by n, that's the width of each trapezoid, so we have n trapezoids. And that's our for loop right there. So xi equals a plus I times h. And approx, that is our, that is right there our That's our approximate area under the curve. And then, once we're done with our calculation, we multiply our approximated area with the width of our trapezoids. So that's how we would write it in code. When you parallelize a program, there are four basic steps. Partition the program solution into tasks, identify communication channels between tasks, aggregate tasks into composite tasks, map composite tasks onto cores. With our OpenMP trapezoid rule program, there are two types of jobs here. Computing the area of a trapezoid, computing the areas of trapezoids, and adding the areas of trapezoids. So again, we're computing the area of a trapezoid, but then we're adding it with the area of all our other trapezoids. Computing the areas of trapezoids does not require any communication between other channels. Even if we rearrange it like this, so we're just adding one of each trapezoid's height. This is still just addition. So, nothing about this part here, nothing about calculating each of these terms requires any communication between threads. It's when we add them up that requires that communication. We're also going to assume that we have more trapezoids than threads, so we need to divide the work by assigning a contiguous block of trapezoids to each thread. So, although I drew it as these big chunky trapezoids, we can imagine dividing it up into even smaller trapezoids as follows. So let's say, if we divide this between 4 threads, we say thread 0 gets this block, thread 1 gets this block, thread 2 this block, thread 3 this block. So again, there is a way we can compute that, and that's by calculating each thread's local starting point and local stopping point. So these are our starting and stopping points for each thread's group of trapezoids. The program would look something like this. So this is split between multiple slides. So we begin with our function prototypes for our trap function. The trap function is so the trap function takes in A, B, and a pointer to our global result. A and B are the starting and stopping endpoints for the area under the curve. N is the number of trapezoids, and global result P, that's a pointer to our local variable global result. Our trap function is as follows. So we have H, that is the width of our trapezoid, X, that is the... Okay, so X is going to be some value along the X-axis. When we do f of x, when we call f of x and we pass in x from this interval from A to B, we're going to get some height. Even though we've overloaded the height to mean the width. Anyway, we calculate our local n to be n divided by the thread count. Our local b to be A plus my rank times local n times h. Local b to be local A plus local b times h. My result to be half the value of when we add the first trapezoid's first height and the last trapezoid's last height. So that is our starting value for my result. And each thread calculates a portion of these trapezoids. So it's basically finding the area of smaller areas. You're finding the area of a smaller area while other threads are calculating areas of their own smaller areas without any overlap. And then it's just a matter of adding all those small areas together to get the final area. So that's what's happening here. So what about that f of x function? So f of x, we can define it to be anything we want, but let's just say f of x equals x squared. If you're gonna be working with this code on a Unix system, swap out scanf. Just use scanf, not scanfs. If you're working on a Windows system, it should be scanfs because security concerns. So before we get to writing this, let's talk about the scope of a variable. So think of the scope of a variable as the region enclosed by curly brackets in which a variable is going to be used. With one caveat, you cannot use a variable before it's declared. So if I write code like this, so if we have this code here, then the scope of thread count is think of it as the region between curly brackets in which the variable is enclosed. So this thread count variable has the scope that is within these two curly brackets, but not before this line of code. If I did something like this, this cannot work because we tried to use a thread before we even declared it. So yeah, that's the scope of a thread. Think of it as a region between curly brackets in which a variable is enclosed. If we have a variable that's within the body of a function, this is function-wide scope. If we have a variable like this, that's file-wide scope. We call that a global variable. With OpenMP, you can have threads that use shared variables, or you can have threads that work with their own private variables. So those are called private scope and shared scope. So, let's just try out this program for ourselves. I'm going to do this on the Linux machine. So I'm going to make a brand new file and new window, actually new tab. I'll just copy that boilerplate code, save as, let's call it trap1. Trap1.c, and we're gonna start writing out the code for our trapezoidal rule program. So this program is gonna work as follows. Now that we have a basic idea of how that trapezoid function is gonna work, the trap function, we pass in for each thread A, B, and N, and each thread is going to calculate its portion of trapezoids. It's going to calculate the portion of trapezoids it's going to add together. So A, B, N. We also pass in a pointer to the global result. So each thread is going to, of course, calculate its portion of the trapezoids. And we call that function within a parallel section. So let's just begin. Int main, int argc, character star argv. Return 0. There we go. Oh, let me add those function prototypes. So void trap double A double B int N double star global result pointer. And we want a function prototype for f of x. So double f double x. There we go. Oh yeah, that hashtag should not be there. So there we go. Let's write the code. There we go. So now we have variables for our result, our left and right endpoints, the number of trapezoids, and our thread count. We're going to say thread count equals str total argv1 null 10. There we go. We're going to also get the number of trapezoids plus our endpoints. So there are two ways we can do this. We can just pass them all. We can just pass all of them in as command line arguments. The example program has us using scanf for that. So we can type it out as this: scanf %lf %lf %d. So I think this might be wrong. It might be slightly different. So when we do scanf, we need to pass in the addresses of the variables that will store our entered values. So address A, address B, address N. Of course, we need to prompt the user. Prompt the user for the endpoints and the number of trapezoids. So, right? F enter endpoints A and B and the number of trapezoids N. Okay. We're now going to call our trap function in a parallel section of code. So pragma OMP parallel num threads thread count trap A, B, N address of global result. Oh, by the way, if you want to run an entire block of code in a parallel section, you would enclose it in curly brackets. So if we want to run multiple lines of code as part of a in a parallel section like this, you would just enclose it in curly brackets like that. Give me a minute. Okay, we're almost done. We just need to print out the result that we got. So printf with %d trapezoids, the estimated area from %f to %f equals %f. And then NAB global result. There we go. So this is slightly different from the slides that I have, but that is just the main function itself. Like, we need to add the code for the trap function, so it's a bit more involved, but it's about as involved as the code that we wrote our pi estimating program. So let's try it out. Void trap double A double B int N double star global result T. So this is a void function, so it doesn't return anything, but we need to declare a whole bunch of variables. Double H, X, and my result. Double local A, local B. We can add some comments for this to this. So local A and local B are the endpoints for that thread's portion of trapezoids. Where H is confusingly the width of a trapezoid and X is x is the x value that we plug into f of x. So h is confusingly the width of a trapezoid, and x is the value that we plug into f of x to get our height of our trapezoid. You see how confusing this is? Yeah. Anyway, int I and local n, we need those for our for loop. Well, we need one of them for our for loop, where local n, I is for the for loop, local n is the number of trapezoids to add. Well, that's actually for the thread. So local n is the thread's number of trapezoids to add. So let's begin running the rest of the code. So h is confusingly the width of a trapezoid equals b minus a all divided by n, local n equals n integer divide by thread count. Oh yeah, we forgot. We forgot to add 2 lines of code here. So that is int by rank equals OMP get thread number and int thread count equals OMP get num threads. There we go. So local n is the thread's local number of trapezoids to add together. So there we go. So local n equals n divided by thread count. Local a equals a plus my rank times local n times h. So that's just to specify where the starting point for that thread's portion of trapezoids begins. Local b is local a plus local n times h. And then we're going to set my result to be half of the first trapezoid's first height and the last trapezoid's last height. So, in parentheses, f of local a plus f of local b all divided by 2.0. I'm dividing it by a float, so that way this doesn't get interpreted as integer division, it gets interpreted as floating point division. So this n is an integer variable, and so is thread count. If we divide an integer by an integer, we get integer division, we get another integer, and we discard the remainder. Yeah, if you've ever had to divide anything in a programming language and somehow you were never getting a remainder or a decimal point answer, make sure you're not using integer division, because this is integer division, where when we divide n by thread count, we just get the result and discard the remainder. This is floating point division, so we get floating point values. Okay, let's write that for loop. For I equals 1, I is less than or equal to local n plus 1, I plus plus. X equals local a plus I times h. So what's going on is this. So what is this local a plus I times h? So we are starting, let's say we're starting at point A here. Let's call it A1 and B1. And you know what, let's just zoom in. We are starting at A1 and we're incrementing by units of the trapezoid width. So this is going to be, if this is A1, then this is going to be A1 plus H. This is A1 plus 2H. And this is A1 plus 3H. And so on, until we get to B. So what's going on here? So that's what's going on there. We're just incrementing by units of n to get different x values that we can plug into f of x. So that's what that x equals local a plus I times h is all about. We use x to calculate the height of the trapezoid at that point. But if you recall from how we rearrange in terms like this, we're really just adding the height to our running sum. Okay, so that is going to be my result plus equals f of x, where f of x is a function that we have not defined yet. So we're almost done. My result equals my result times b. And then we're gonna add, so my result is the thread's area for its portion of trapezoids. We need to add that to the global variable. And to do that, we're gonna say star global result p plus equals my result. Now, we're not done yet, because this is a global variable being accessed by multiple threads. If we left this as is, we would get a race condition. If we get a race condition, we risk having data loss. And if we don't enforce mutual exclusion here, we're gonna get the wrong answer for the area. So to prevent that, we need to make this into a critical section. There is yet another directive for that. That is # pragma OMP critical. So that line of code makes a critical section. So remember how we worked with mutex locks in pthreads? By using that one directive, we implicitly made a lock that threads can access and release when they're done. And all that without having to write a definition for a mutex lock, having to initialize it, and having to destroy it when we're done, and all without having each thread call the appropriate acquire and release functions to acquire and release the lock. How neat is that? All that from one line of code. All that from, not all that for a drop of blood, all that from a drop of blood. Anyway, we're almost done. We just need to define what f of x is, and that is, we're just gonna say it's f of x equals x squared. Double f double x. Return x times x. That's it. Alright, so now let's compile our program. Clear? ls, so I can see what code we have. That is trap1.c. I'm going to compile our program using the same command as before, gcc-g-wall-f-openmp-o. The name of the executable will be trap1, and the name of our source code file is trap1.c. Okay, we do have a few errors that we need to resolve though. And the first one is, looks like I forgot a comma somewhere. Comma chameleon. There it is. Okay, let's see the rest of these implicit declaration. Okay, I think, looks like all those errors stem from the fact that I forgot to write a comma in this function prototype. Let's clear, recompile. Okay, there we go. So now, all we gotta do is run a program. If I type in just trap1 by itself, I get a segfault because I never specified the number of threads. Clear. I said clear. Let's try that again. I did it again. Let's try it again, but I'm gonna say 10 threads and enter endpoints A and B and the number of trapezoids n. Let's go with endpoints 0 and 10, and let's do 10,000 trapezoids. With 10,000 trapezoids, the area from 0 to 10 is 334, plus other stuff. Okay, so let's make sure we got the code working as expected. So my result equals my result times b, a global result p plus equals my result. Okay, so I went as far as to punch it into an online calculator to see whether I got the right result, and it should be 333 and 1/3. My result is like off by several orders of magnitude, so I want to go ahead and bug fix this. So, okay, I find the problem. That's supposed to be multiplied by h, not multiplied by b. Okay, let's try that again. Recompile the program. Trap 10. Enter endpoints A, B, and number of trapezoids. Let's go with 0, 10, 10,000 trapezoids. Okay, so now we got a more sane result. 334 units, when the expected answer per that online calculator should be 333 and 1/3. Okay, so it works, but you know how the trapezoid rule works if you remember integral calculus. You start with a quantity of trapezoids that's fairly small. So let's go with 0, 10, 1,000, and we get a crude estimate of the area under the curve. If we did it again with even more trapezoids, that is, let's say 0, 10, 1 million, we get a much better estimate of the area under the curve. And in the limit, where we did this with infinitely many trapezoids that are all infinitely thin, well, it's not that they're infinitely thin, it's that they're approaching infinitely many trapezoids and infinitely thin trapezoids. We're approaching infinitely many infinitely thin trapezoids. In the limit, we get the exact answer of 333 and 1/3. Okay, so it works. Our calculator works for the function f of x. Okay, so the thing is, this is actually part of your first programming assignment with pthreads. So, no, not pthreads, OpenMP. So let's look at your assignment here. So, your first OpenMP programming assignment, you are to write a hello world program in OpenMP. And use the code of a hello world program shown below. Run it with an arbitrary number of threads specified as a command line argument. So I'm just going to write the hello world program here. So that's part 0. Part 1, you are to write the trapezoidal rule program as I had shown just now. So, programmed here just now. You're going to write the trapezoidal rule program with the trap function f of x here and all this main code here. And I want you to show that it works by finding the area under a curve from endpoints 0 to 10 using 10 threads and 1 million trapezoids. So that's part 1. part 2 is modifications to the same program. So I'll show you what I mean. So parts 2 and 3, you are gonna modify. So parts 2, 3. Hold on. So parts 2, 3, and 4, you are to write the same program in different ways. So they are all subtle edits. So once you have this trap function here, all you gotta do is copy paste the code. All you gotta do is make a few copies of this trap 1. And then we can modify it for parts 2, 3, and 4. Okay, so I'm gonna do just that really quick. So let's do trap 2, where we modify the program a little bit, where instead of having a global variable store all of our results, we have the trap function return a value. So here's how it works. For that, we're gonna not have a void function, we're gonna have this trap function return a double. And now we don't need this double global result p anymore. It means now we need to rewrite our trap function down here. So this is the function prototype, this is the actual function declaration. Double, trap, double A, double B, and N. Right, erase that. And due to the nature of this, we don't need a critical section in here anymore. And instead, we're just gonna write in this. Return my result. In the main function, because trap now returns a return value, we need to store that in our global result. So all we gotta do is write in the following. Double global result plus equals trap A, B, and we don't need this global result to be passed in anymore. There we go. But now that is a critical section now, so we need to add in pragma OMP critical. There we go. So your goal with this second part of the assignment is to make these following changes and verify that your program still works. So we're gonna recompile this new program that's called trap 2. Okay, so there are a few things we have to fix up here. So double global, right. I'm trying to redeclare a variable and I shouldn't be doing that. Clear? Okay, pragma. Okay, so hold on. Warning, ignoring pragma OMP critical. So. I misspelled it. So that's a critical section. You gotta make sure your critical section is spelled properly. Let's try again. Okay, there we go. So the changes that you're to make with part 2 are where you rewrite the program. So instead of the trap function returning nothing, you have it return a value that you increment to the global result. That's why you also need a critical section, because we're using a variable that's being accessed by multiple threads. Therefore, we need to make that a critical section to enforce mutual exclusion to avoid having a race condition. So it's literally the same program except for those small changes. So if I run the program now with 10 threads, endpoints 0, 10, and 1 million trapezoids, I get the same result. So what is mentioned in the book is the fact that if you write it like this, because of the nature of how this code is written, it is set up so that only one thread at a time will calculate. It's basically set up so that only one thread at a time can call trap. Which isn't good, because now we have the program running no better than a single-threaded program, which is antithetical to what we're trying to do. Get this program to run with multiple threads. It is running with multiple threads, but we tripped ourselves into having it run multiple threads, but still one thread at a time. We want to have all these threads run all at once. So the fix for that is talked about in part 3. Full disclosure, I tried to time whether I could observe a difference, but I was unable to see that difference for myself. So either I'm doing something wrong, or if I got, either I'm doing something wrong with the time command, or I'm not getting the right times for it, or something about OpenMP is smart enough to implicitly know this is supposed to be multi-threaded. Like calling the trap function should be done concurrently. So yeah, full disclosure, I was unable to observe a speed difference between this and doing this. So, what this does is it does the same exact thing as before, except we are calling trap outside of the critical section. Remember, the code that is within a critical section will only run for one thread at a it can only run for one thread at a time. If we remove the trap function outside the critical section and have it stored in an intermediary variable called myResult, now every thread can do this code at once, but when it comes to adding it, that's still a critical section, but we are still having threads do their work concurrently in parallel. Concurrency and parallel aren't necessarily the same thing, even though I just said concurrently in parallel though. Anyway, the point is, this rearrangement of code will do the same exact thing, except under the idea that if you write it like this, trap will now be called by every running thread. The only thing that's still a critical section is adding those results to the global result. So this should result in the same result. I saved that as trap 2 when this really should be trap 3. So let me fix that really quick and save this as trap 3. And if I want this to be trap 2, save as trap 2.c. So yeah, we are making multiple programs, we are making multiple copies of the same program, but then changing each one a little bit to show that each change works as before. So we're gonna reopen our trap 3. Do you even have a trap 3? Yes, I do. There we go. So let me just reopen all my programs. Trap 1, trap 2, trap 3. So trap 1 is the original program. Trap 2 is where we modified the program so the trap function returns a return value, but it's set up so that the call to trap is within a critical section. If the call to trap is within a critical section, then only one thread at a time can call trap. If we put the call to trap outside the critical section, then every thread will be able to call trap. This leads to multiple threads running trap at once. This leads to each thread calculating its portion of trapezoids in parallel. So that's a third modification. So if we want to show that this works as well, we would compile this program, run it with the same number of threads and trapezoids with the same endpoints, 0, 10, 1 million. And yeah, it works the same as before. So that's all there is to it, right? Well, the thing is, OpenMP has a few neat tricks up its sleeve. So we were in parts 2. In parts 1, 2, and 3, we added in a critical section, but the thing is, OpenMP has a few tricks up its sleeve that allows us to write code without having to declare a critical section. It's called a reduction operation. We need to declare we have to specify a reduction operation and a reduction variable. What's that? Okay, so let's talk about that. So it's an alternative way to write our trap function. Instead of having a call to trap followed by adding the return value to the global result within our critical section, we have a reduction variable and reduction operation declared. So a reduction operator is it's an associative binary operation, and a reduction is a computation that repeatedly applies the same reduction operator to a sequence of operands to get a single result. So what does that mean? If we are to add, if you wanted to write code that would add all the values in an integer array, so A0 plus A1 plus A2 plus A3 all the way to AN, for example. We are doing that A0 plus A1 plus A2 plus A3 ... all the way to AN. We are storing that result in some variable called sum. Sum is a reduction variable. In a for loop, we say sum plus equals AI, where AI is some variable in our integer array. It's some element in our integer array. So we are repeatedly adding to our sum value. Addition is our reduction operation, and sum is our reduction variable. So when we have this for loop where we repeatedly increment our sum by one element in our integer array A, we are performing a reduction operation of addition to a reduction variable called sum. And this is important because that's exactly what we're doing here. Look. We have our global result being operated on using addition repeatedly. We have the global result acted on. We are adding to our global result repeatedly. Each thread is doing a operation of addition, adding to the global result my result. So global result is our reduction variable, and addition is our reduction operation. Okay, so that's all fine and dandy, but what does this do with our code? It means we can get rid of the critical section. Here's how. We add another clause to our pragma OMP parallel directive here. We write in the following: reduction, left parenthesis, the operation is addition, so plus, and then colon, the reduction variable is global result. So this is a stand-in for having a critical section like that. But now that we don't need a critical section, because we are repeatedly doing addition, what it means now is not only do we not need the critical section as we had before, but because we had to rewrite the code as follows to be this by adding a reduction clause, it means all of these additions here where we had to split this one line of code into 3 lines of code, we don't need to do that anymore. So this is part 4 of your assignment. So I'm going to save this as trap4.c. in the original code here, we had global result plus equals trap APN. We split it into 3 lines of code under the presumption that trap would be called by one thread at a time because it was in a critical section. But we didn't even need to write a critical section anymore. All we gotta do is copy this 1 line of code, paste it in here, and that's it. So this is the last modification you make in part 4. So really, your first assignment is just write the trapezoidal rule program after you write the hello world program, and then modify it 3 ways to show that each change works the same as before. So let's get to the chase. And just compile our last trap program here. There we go. And if I type in trap 4 and pass in 10 threads, I'll do 0, 10, and 1 million for endpoints 0 to 10 and 1 million trapezoids. And just like that, we still get the same result as before. But is it any faster? As I mentioned, I tried to time how long this program works. I tried to time how long this program runs using the time command, and I was unable to find a appreciable speed up between trap 1, trap 2, trap 3, and trap 4. Not that there isn't a speed up, but I was trying to determine whether the code for trap 2 would have resulted in an appreciable slowdown, and I was unable to find such slowdown. Either I'm doing it wrong and I should be using some different command, or somehow OpenMP is optimizing the code for me behind the scenes. So that's just one thing that I just unable to observe. But the point of all these changes is that we can get our program to work with minimal edits. So really, the point of all of these directives is to obviate the need of writing so many lines of code, to obviate the need of having to write so many lines of code, to obviate the need to have to split up our code like this. By writing just that, we perform the same. Okay, so by writing our code like this, is to do the same thing as this commented out block of code. The point of OpenMP is to make it easier to write multi-threaded programs. The fact that we have a reduction clause means we can parallelize code with minimal edits. And to me, that's the beauty of OpenMP. But we're actually not done yet. There is a little bit more to discuss here, and one of them is the parallel for directive. So that's already section 5.5 in the book, but I'm not going to talk about the parallel for directive just yet. Rather, I'm going to save that for next week. The parallel for directive is, in my opinion, one of the most powerful tools that is available in OpenMP. With a parallel for loop, if you have a for loop that you can parallelize, instead of having one thread do one for loop iteration at a time, you would have a team of threads, each doing different for loop iterations at a time, and then adding to a global result. I really want to show you what the parallel for directive does to a for loop, but again, I think I want to save that for next week. So this is your first assignment for OpenMP, where you write the hello world program as shown here. You write the trapezoidal rule program as shown in part 1. You do it again in part 2, where you make the changes to the code shown here. Do it again in part 3, where you make these changes here, and do it again where you undo all your changes, revert to part 2, and then slap in a reduction clause. So the point values are actually off. This one's supposed to be 10 points. So, yeah. Really, it should be 5 points per part. So a screenshot of the program running from part 0, and then for parts 1, 2, 3, and 4, the source code and a screenshot of the program running. Since you're making rather minimal changes to the code, you can instead opt to screenshot just the part of the code that you edited. So those are the deliverables for OpenMP Assignment 1. And that, I believe that is due next week. So this video is also the instructions for your first OpenMP programming assignment. Okay? Alright, if you have any questions, let me know. We can talk it over via email, or if you want to, we can talk it over Zoom. So this is your first programming assignment. I'll be getting to grading all your assignments in due time. It will take some time though because of how many assignments there are though. But anyway, that's gonna be it for our first look into OpenMP. If you have any questions, hit me up via email or Canvas message. And with that, I'll leave it to you, and we'll meet up next week. Alright? Okay.